There we go. Okay, so yeah, last time we took a step back from the computer, and we're talking about these 7-segment displays. And don't worry, we're going back to the computer, because ultimately we want to hook this into the computer to output some values that we have. And we were talking about the 7-segment displays and how really we have these, each of these takes 1 byte effectively, but the bit patterns are going to be, there's a mismatch, right? Like the bit pattern to output the number 1, or 0 even, the bit pattern for 0 is 00111111, right? Just by the nature of how that 7-segment display works. Each input is either turning on or off a specific segment. And then we also saw how, is this really as wide? Oh no, there we go. Then we also saw how, well, you know, if we have 1 byte words, like if we have a total of 8 bits, we can represent up to 256 values, 0 through 255, or negative numbers as well with 2's complement. So with that idea, we realized that we actually need 3 or 4 if we're dealing with the negative sign. But we need 3 7-segment displays, meaning we need to actually map every single one of those 256 bit patterns to how many bits was it for, do we remember how many bits do we need for the 3 7-segment displays? 24. Right? 8, 8, and 8. And then I was like, well, really, it's 25 because we'll have that extra one for the negative sign, but we'll talk about that later. So, an example. Here's a 3-bit, or sorry, this would be 123. The bit pattern for 123 is 0111111, right? But that would have to map to, I'm guessing in order, okay, 00000011011011101001111, of course, obviously, right? And I knew that just because I was saying 000001100101 and so on. Because remember, that was the order that we defined our bits, where this was the most significant bit and that was the least significant bit. We could have done it in reverse order. Doesn't really matter. And then here I was showing like, well, the 4th one for a little negative sign. We could do other things for like the negative sign. What we could have said, if we really wanted, if we were really worried about components, like if we were physically building this and the cost of another 7-segment display was just too much, we could have done something where like, well, the decimal could be on if it's negative or something. Like we could have done something else, but we're using a simulator, every component's cheap, whatever. We could just do a little negative sign, it's nice. Cool. And we also actually have to answer the question, if I have the number 3, I have 4 7-segment displays. And I have the number 3. No, yeah. Right there, 3. Okay? We have a decision to make. Does anyone see the decision we have to make here? Yeah. We have a choice. We don't have to do this, but you'll see shortly that this actually makes the design a little more systematic. Is really, we should probably say like, zero, 0, 3 for 3, right? We will pad it with leading zeros for our 3 digits. Okay. All right. Now we could use a programmable logic array, and as we discussed last time, nope, we're not going to do that. It's too tedious. It's too painful. This is for 4 bits that control 1. We would need, like this would be, what did we say? 2, 4, 8. It would be 16 times larger if it was 18 bits. Or sorry, if it was 8 bits. So yeah, we're not going to do that. We'll use a lookup table, but there's a problem with the lookup table. Like with the lookup table, I don't need to build the hardware, but what I do is I go to each, like, okay, this is 0, 1, 2, 3, 4, 8, 9, 10, 11, or 8, 9, A, B, C, and so on, right? We could think of these as each like a row, but it's set out in like a table, just each one. Each one of these corresponds to when the input to the lookup table is, let's say, 4, we go to this cell. And that's the 25-bit pattern we output. Here, you'll be like, but that's only 8 bits, 2 hex. I know, but this is just for demonstration purposes, okay? So I would need to go in here and put the 25-bit pattern for every number, the corresponding cell's number, in there. If I were to go find 123, it would be whatever that was, 0, 0, 0, 0, 0, 1, 1, 0, the 25-bit pattern for that. Better than making a programmable logic array, maybe, but kind of a pain in the butt. So an alternative is, well, we can actually load a hex file. A hex file is just a data file filled with hex numbers. It can actually be binary numbers if you prefix it, and it can be decimal too, I think, technically, but hex numbers. And annoyingly, the first line in the hex file has to say v2.0 raw. Again, like I said last time, I think we need to blame Intel for that. It's a hex file. It's just a text file, but instead of .txt, it says .hex. And in it, you'll have stuff like this, right? So what values are in there? 3F, 6, 5B, 4, 6, or 4F, yada, 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 right? There we go. So we can generate a hex file that looks like this. If we generated a hex file like this, we would have 256, well, 257 rows. Each row corresponds to the input, like the row number, the line number, starting at 0, really. The input to the lookup table would be which line to go to, and the data at that would be the 25-bit pattern, or like, let's just say 24 bits for simplicity. 1, 2, 3, 4, 5, 6 hex digit number. Cool. Yeah? Is that clear? Now, okay, this is maybe kind of better, but are you really going to go and write the number for each? No, we're not going to do that. Instead, what we'll do is we are going to programmatically, we're going to write a program to generate this for us. So to make our lives a lot easier. And we're going to write a simple little Python script to do it. Now, before we jump to that, though, so treating the lookup table, by the way, yeah, just to remind you, the lookup table, it's just like a map. It's like a dictionary, okay? Input, output. It maps some input bit pattern to an output bit pattern. The number of bits on the input and the output do not need to match. The number of bits on the input is the number of unique identifiers we have, and the number of bits on the output is whatever the hell we want it to be. So, yeah, in the above example, the key 3 maps to the value 4F. 0, 1, 2, 3, right? We can import this hex file into digital. So if we go to, okay, let's say component, I think it's in logic. Yeah, lookup tables. They put it in logic, even though it's, by the way, you may have thought to yourself, hey, this lookup table is kind of like RAM or ROM, where it's like a memory address and the data. You're right, it effectively is. In fact, in practice, what people would do to create a lookup table like this is use a ROM chip. Now you might be like, okay, ROM, RAM, I know they're both memory. RAM is designed for, it's designed for frequent access read and writes. ROM, it's the same idea. You can do the same thing, but the hardware is designed not to have a lot of writes. There's something about the underlying hardware where the spirit of the idea is you don't do a lot of writes. You can write to ROM, but you're kind of supposed to set it and forget it. So ROM is a perfect example of a lookup table. Now, why did we put the lookup table under here in digital? Why under like the logic and or blah, 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 blah? I don't know for sure, but my guess is, remember when we learned about lookup tables, they're effectively a quick and dirty way of doing a programmable logic array, which is any logical function we really want to create. So that's my guess. I don't really know. If we right click on this, data edit, you can go in here, edit the data in there. If we go here, number of input bits, what did I say it was? 8? Nope, what did I say? What did I do wrong? Ah, there. I said 28. Whoop. Well, I guess it looks like it maxes out at 20. 8. There. So now I go in here, edit. I can go and edit all these things. right? Obviously, the number of data bits, well, there would be 25 because of that sign bit. Edit. Like I was saying, though, we don't want to go do all this. What we could do is we could do file, load, and then we can specify a hex file, which is just a text file. You could actually save it. So if here, for fun, let's do 44. Great. And down here, we'll do 88. Cool. There. Again, why is 88 58? Because hexadecimal. We could save this. Save. I'll just save it to my desktop. ASD hex. My marker. I don't know why it's not recommending Notepad++. This is so annoying. Just once. Whatever. There we go. Huh. I've never seen this before. 85 times 0. I wonder if it's saying I wonder if this is some interest. I've never seen this before. I'm guessing because I have so many zeros, I'm guessing this is like a shorthand for, say, row 0. I don't recommend doing this because I think it would mix you up quite a bit. But 24 followed by 85 zeros followed by 58. Yeah, I see your face going like, ugh, yeah. First of all, I don't actually know that's what it's doing. That's my guess. I've never seen this before. But this would definitely spoil the whole, each line, And our line numbers are already off, so. Anyways, long story short, you can save it like that. And similarly, we can load things in. Now, you may notice, actually, so here's the general design, okay? Here's what I'm gonna do. I've got my 4 7-segment displays, each hooked up to the output of this. This is my lookup table. It has 9 inputs. Hold that thought. And it's just the data inputs, okay? Least significant, most significant, most significant. Here we've got 1, 2, 3, 4. These are just probes for testing purposes. We would not be including this in the actual computer we're doing. I've just got them there so we can observe the values on the signals to make sure everything's working correctly in the tests, by the way. And you'll also notice, okay, so this is outputting 25 bits. 8, 8, 8, 1. All of these, every one except for this last signal here, which corresponds to that part of the 7-segment display, are hooked up to 0 because we never want anything else on. And this signal here, I know it might be confusing, but you'll notice they're not connected here. And then this will be controlled by whatever that 25th bit is going to be. If it's 0, it's off. If it's on, it's on. It's interesting. You'll notice I have to use a splitter in an interesting way here. I didn't need to use it this way. I just thought this was the cleanest way to create it. Take the 24 bits, 8, 8, 8, 1. I made a splitter that does 25 to 8, 8, 8, and 1. The 1 goes down there, and it's observed. The least significant 8 go here. It gets split into the top 4 for here, the bottom 4 for there. That's the design. Cool? Cool? Happy? Sad? Awesome. Now, I will go into more detail on this, but you'll notice that I added an 8th or a 9th input bit. Okay? Think about it like this. I'll give you the idea. Imagine we just have the 8 bits. Okay? So I have 0, 0, 0, 0, 0, 0, 0, 0. That maps to 25 bits for 0. Right? I see 0, 0, 0, 0, 0, 0, 0, 1. That maps to right? And so on. 0, 0, 0, 0, 0, 0, 1, 0. That map 0, 0, 2, right? Happy so far? Yeah. Eventually, I get down to 1, 1, 1, 1, 1, 1, 1, 1. And that maps to 2, 5, 5, right? Can you all see this decently? Yeah? I have 256 here. Okay? But that's only 8 bits. And I'm showing you, and by the way, pay special attention because what I'm about to do is a perhaps obvious trick, but it's a trick nonetheless, and it's a very important trick we're going to make use of. The problem I have is, well, I want to be able to do signed and unsigned integers. These are unsigned integers. 0 through 255. There's no negative numbers. They're only positive, right? So what I could do is I could have an 8-bit input lookup table for the signed integers and another 8-bit lookup table for the patterns for the unsigned, and then the pattern for the signed, right? And then I can use like a multiplexer to be like, well, depending on, do I want to output a signed number or not? I could use like a multiplexer to select, do I want the output from the unsigned or the signed, right? I could do that. Or I can just kind of cheese it by being like, that 9th bit, and then 1, 0, 0, 0, 0, 0, 0, 0, 0. That maps to, well, that would be 0. Right? 1. So this 9th bit is acting almost like a multiplexer selection bit. Which block, like look, obviously with 9 bits I have 512 unique values. But I'm treating it as a selector bit to be like this block of 256 or this block of 256. When it's 0, it's the 0 through 256. When it's 1, it's 0 through 255. When it's 1, it's 256 to 511, I guess, right? But really, it's the second batch of 0 through 255. Or really, 0 through 127 and then negative 128 to negative 1, right? So really, the second batch is actually broken up into like 128 numbers followed by 128 numbers, right? The positive and then the negative chunk. Yeah?
Would that mean there's overlap with unsigned and unsigned?
What do you mean?
So, like, if we're treating unsigned as like positive, then if we just toggle signed, then we only add like half as many.
We could, but that starts to create way more logic where we've already got the hardware's cheap for us. We're just gonna, the numbers through 0 through 128 here, and the numbers 0 through 128 here, but preceded by a 1, are gonna be the exact same output bit patterns. You're right, that's kind of like, wow, we're wasting RAM, but we'll just repeat them for the sake of ease. If it's not quite clear to you, wait for the script and how I'm generating the hex file, and I think it'll become a little bit more clear. But do we have any questions about this idea? Even though this 9th bit is acting like a selector bit in a 2-input multiplexer, a 2 to 1 out, 2 in, 1 out multiplexer, we're just adding it to the lookup table. That's it. And we save ourselves having to build a whole new multiplexer. Which I think is pretty cool. But this idea of like, oh, we need a selector bit. We could have 2 lookup tables in a multiplexer. This idea actually comes up frequently. And we're going to be using this strategy several cases where different segments of the input of a lookup table, like maybe like x, Y, 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 Z, Z. Like, we have an 8-bit input to a lookup table, but these 2 bits mean something. And these 4 bits mean something entirely different. And these 2 bits also mean something entirely different. But altogether, it maps to 1 row in that lookup table. But like their meaning is different. But remember, it's all about that data encoding. What does it mean? They're just zeros and ones, low voltages and high voltages. Okay. Last chance. Any questions about any of this? Yes?
So the numbers that are signed, those aren't using like two's complement?
They will be 2's complement such that like row, the row that corresponds to like 1, 1, 0, 1, okay, 0, 1, 1, 1, 1. I would decode this as a 2's complement number. Like, what 2's complement number is that? I don't know if you can see it. So like 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. So this here means the first, that 9th bit, that most significant 9th bit, really is that sign like selector, state bit, or whatever we want to call it. And this right here, 1, 0, 1, 0, 1, 1, 1, 1 in 2's complement means something. I don't know offhand, right? Now, if it was unsigned, it would mean a different thing. And I know that because this most significant bit here, that 8th bit, well, depending on how you want to count it, but that bit, the most significant after the sign bit, tells me it's a negative number. So I know that the pattern, if it was signed versus unsigned, is different. In this unsigned chunk, I would map to what is the output, the 25-bit output pattern for 24-bit output pattern, because I know I don't need that signed bit. I know I don't need this one to be on if it's unsigned. That pattern, those 3 digits, like here, somebody look up, what is 1, 0, 1, 0, 1, 1, 1, 1 in 2's complement? Well, that's, okay, it's easy. Remove the 1, 0, and that would be 0, 1, 0, 1, 0, 0, 0, 1. So that would be 1, 2, 4, 8, 16, 64, 70, 81. 81. That should be negative 81, I'm guessing. But if it was signed, if it's unsigned, it's not 81. It's 128 plus 32 plus 8 plus 4 plus 2, whatever that is. So the bit patterns for the 7-segment displays are entirely different based on, am I interpreting this bit pattern as a signed or unsigned number? Is that clear, more clear? Again, I think once we start generating the hex file with a script, it's going to be a little clearer. Maybe not, I don't know, we'll find out. But let me know. If it's unclear, ask now. So that means everyone's happy. Okay. All right, so the lookup table takes 8 input lines representing 8-bit numbers. Additionally, the lookup table will have 1 additional input line to specify if a number is signed, if the number is 2's complement. Basically, when this is on, I need to interpret this as a signed 2's complement number. When that's off, I don't care about 2's complement. I interpret it as an unsigned number. Thus, the lookup table has 9 input signals. We map these input signals to the corresponding 7-segment display patterns for the output. For example, the number 10101010 would map to the pattern to display the decimal number 170, but the number 10101010 would map to the pattern for negative 86 if it was signed, right? So you're like, but the inputs are the same. Well, to the lookup table, there would be a difference to the input. There would be a 0 preceding this, and there would be a 1 preceding this, meaning that's 2 different rows. And the patterns would map to the patterns that make a 1, a 7, and a 0. And this would map to a pattern that does a negative, a 0, an 8, and a 6. Since each digit uses 8 bits for its display pattern, there are 3 digits. A total of 24 bits are needed, but there's the additional sign that we'll do the little negative sign. But we're only going to use one of those signals. We don't need a whole 8 bits. And then just to say, oh, of these 8 bits, they're all 0, but that one. No, we'll just use 1 bit. That's either on or off. Notice in the design that only one line from the lookup table is connected. Yeah, specifically this one from the to G. Thus, 25 output bits. Is that clear why there's 25? Right? What I was saying was I could, if I wanted, and I could output 8 bits for that fourth one and map each of those 8 bits to the 8 input signal lines for that fourth digit that only ever show, like if this is it, that will only ever show this, which is this signal here. I could connect, like I could output 8, 16, 20, 32 bits, 8 for each of the 4 7-segment displays. But they're always going to be 0, except for this one, which may be a 0 or it may be a 1, if it's signed or unsigned. So to save space, we'll just only care about the 1. All of these are connected to nothing, to ground. And this will be connected to the lookup table where we control on or off, on or off, on or off. Okay. There. So let's create the 7-segment display pattern. Now, I've created this script in such a way, not that you're going to be like, here's the natural way I would think about it. I've kind of created the script to be like, here's a script to generate it. And let's not think too hard about it, because I watched some videos on somebody building this, and I put some thought into it, and I cleaned it up and made it this nice, clean way to do it. So here we go. All right, so what we're going to do is we're going to start with a couple of constants that correspond to the bit pattern for every one of these numbers. Okay? So I'm going to create a constant that is 0. This is Python, by the way. A constant called 0. All right? And the bit pattern for a 7-segment display to output 0 is this. Now, I don't know if you know this about Python. In Python, I could type the number, what is this? 1, 2, 3, 4. So that's 16 plus 32, no, 15 plus 8, wait, okay, 1, 2, 4, 8, 16, 30. What's 32 plus 16 plus 8 plus 4 plus 2 plus 1? Whatever that is, I can type a decimal number. Like as far as Python concerns,
It's one less.
you're right, it's 1 less than what this is. 63. So that'd be 63. Perfect, perfect, good. I was testing you. So 0, as far as Python's concerned, it's like, okay, I made a constant called 0 and it's got the value 63 in it, right? That's all Python cares about, is it's an integer. Python doesn't give a shit. Python cares about the value, not the encoding, the value. It knows what 63 is. It doesn't care if you're representing it in base 2, hex, 10, whatever. It doesn't care. It's a 63, right? Now, I, as the programmer, look, it's a 7-segment display where each of the 8 bits signals corresponds to something being on or off, so I'm representing it as the binary pattern for that 7-segment display. So I could write 63 here, but if you would come along, you'd be like, 63, what the hell's 63, right? Here you see, okay, oh, it's a bit, okay, it's the bits matter, okay? That's the idea. So these are the patterns, the 8-bit patterns for each of these digits. Cool? Cool. I also include their hex here because why not? Don't ask me why I didn't include the decimal though, because that also, I guess, would have made sense. Then I'm creating a list that just contains 0 in the 0 index, 1 in the 1 index, 2 in the 2 index, and so on. They go all the way to 9. Cool? Any questions about that? All right. Now, I'm going to warn you. I'm about to make use of several bitwise binary operators. These are all things I know you are familiar with, and if you're not, you will be familiar with half a second of thought into it, okay? But you probably don't do this stuff very often. You go back in time not that long ago, these types of operations happen all the time everywhere, right? This is how you did programming, right? You move bits around and crap, right? Well, we don't really do that anymore because we're several layers of abstraction programming in Java, right? And Java compiles to bytecode, which runs on a virtual machine, which is written to run on your CPU, which then has an instruction set that goes and controls all the hardware on the CPU. There are a lot of layers of abstraction between here and here. We're learning about these layers of abstraction right now, though. So remember that. So anyways, we're going to be using bitwise operators. So here, great. There is the digits. These are the bit patterns for each of the digits. Now that's great and all. I can generate the bit patterns for all the numbers 0 through 9, but I need 0 through 255. So how am I going to do it? Well, I got a nice clean way to do it. It looks like this. But before we jump to the code, let me explain the idea. So, to create the 25-bit output patterns, we're going to use two bitwise operators. One is called bit shifting. Raise your hand if you know what bit shifting is. Raise your hand if you don't. Okay, that doesn't make any sense to me because about 1/3 of the class raised their hand for saying they knew what it was, and then no one raised their hand for saying they didn't know what it was. So I don't understand. Because they're embarrassed. You should be. A bit shift, you don't be embarrassed no more. A bit shift is literally this simple. There, I've got an example of it right there. The binary pattern, 0, 1, 0, 1. This right here, this is the Python operator. Other languages use this. This is the operator for a left shift by 4. So what do? I just move them over 4. Now, you might say, but how do we? Well, you add like these padded zeros. That's all it is. If I had the pattern 0, 0, 0, 1, and I bit shifted it to the left 1, I would have the pattern 0, 0, 0, 1, 0. I'm including the leading 0. I guess I don't really need to, but I am. So, makes sense? Basically, move these to the left 4, but every time you move when you add a 0, so the places still exist. If I move something to the left 4, can anyone tell me what happens to the value, like the actual, the integer value of what this is? Divide by 16? Multiply by 16, yeah. You move it once, we double it. Which you all learned from lab on Wednesday, getting angry about how stupidly simple you did a bit shift. You did a bit shift by 1, which doubles, but anyways. This is the same as multiplying it by 16, by the way. That's a left bit shift. There's also something called a right bit shift. Who wants to guess what the operator would be? The other way. Very good. Instead of less than, it would be greater than, which, think of it as the arrows. Which way are we going, right? And you right bit shift, okay, you right bit shift. Cool. Awesome. The other thing we're going to do is bitwise OR. Right? Bitwise OR is just OR on the bits. So bitwise OR of these two values would be, you do each pair to generate 1. So 1 or 1 is 1, 1 or 1 is 1, 0 or 1 is 1, 0 or 1 is 1, 1 or 0 is 1, 1 or 0 is 1, 0 or 0 is 0, 0 or 0 is 0. Bitwise OR. Now, you might have never noticed this before, but in Python when you're writing your Boolean operators and you want to do OR, you type OR, right? You want to do AND, you type AND. But in Java, we do ampersand and pipes, right? You do that in Python too if you're doing the bitwise operators, right? See, it's the pipe, right? Neat, right? Cool. you don't think that's cool, I don't know what's wrong with you. So here's what we're going to do. All right. Okay, yeah, let's finish with this thought too. Here's another trick that we're going to use to generate our three-digit 25-bit, 24-bit unsigned integer patterns, okay? The reason I keep saying 24 for the unsigned is because that 25th bit really doesn't matter for us, right? So here's the other thing, which some of you, I can guarantee maybe half of the people in the room have solved this problem on like Caddis or some other like cheesy programming practice thing. It's a common problem. Given a number, like 1, 2, 3, tell me each individual digit, okay? I want the individual digits. How do I do it? Well, here's how we can do it, right? You take the number, you divide it by, in this case, I want to get the hundredths digit. I divide it by 100, so that divided by 100 is 1. Now, actually, I want, yes, you'll notice I do slash because I want proper division, not nonsense Python being helpful division. So 1 divided by 100 is 1. How many 100s can I get at 1? Right? I take that value mod 10. Therefore, the 100s place is 10. Now, you might say, well, that one didn't really feel necessary. It'll feel, I just have that there for consistency. Okay? 1, 2, 3 divided by 10. How many groups of 10 are there? Well, there's 12 groups of 10. Right? 12 mod 10 gives me the 2. Therefore, the 10's place is 2. And then finally, 1, 2, 3 divided by 1, not strictly necessary, but you know, keeping it consistent in general. How many ones are there? Well, there's 123. Mod 10, to only get that last, the last value out of it, we get the 3. Therefore, the 1's place is 3. Here, I'm not generalizing. Here, I'm just strictly doing it for 3-digit numbers because I know all my numbers are going to be at most 3 digits. So I don't need to be like, I spent far too long making the script not crazy complex, but unnecessarily complex to work with arbitrary length numbers. And then I was like, screw it. I'm making it so much more complicated than it needs to be for 3-digit numbers. If this is unclear to you, you can figure it out later. But basically, this math checks out, okay? If you follow these steps, you could get this place, and this place, like the individual values there. So if I have a way to tell me what the 100th digit is, and I know what the 100th digit bit pattern is based on those constants, and I have a way to get the 10's digit and get its pattern, I know, and the 1's digit and get its pattern, I'm all set. But then again, at that stage, like I just have 3 8-bit patterns. I need to combine it into one big thing where their place matters. But we know about bit shifts. And we know about ORs. I know. I want to be very clear about something too. Okay, I'll finish this and then I'll come back to this clarity thing. So with this idea, take each 8-bit number, obtain each place, the best explained with an example. Consider the number 1, 2, 3. We have those patterns, right? I know I have a 1, I know I have a 2, I know I have a 3. These are the 3 8-bit patterns, okay? But really, I want one big 25-bit pattern, right? Where this is the most significant 8 bits, then this, and then this. So shift the 8 bits for the 100s over 16. So, shift this over there. So we have 8 bits followed by 16 zeros. Here I have 8, I guess, remember, there's an infinite number of leading zeros. Who cares? My bits I care about followed by, well, here, let me do it over here. I have that followed by 8 zeros. And then this, which is there, right? I shift it to the left 0, right? So that's what I'm going to do to get that. Cool? I just did bit shift. I bit shifted this 16, 8, 0. You might say, why bit shift 0? Fine, don't. We leave it alone, fine. Then all we do is just OR these together. Now you might say, okay, do we really need to OR because it's always 0 or whatever? Yeah, that's the value of OR, right? This is just a nice way to kind of like smush them together. Like, okay. This is a 1, look, 0, 0, oh, it's a 1, right? Like, I shouldn't have to explain this. You get what I mean, right? We OR it together. There, I'm just saying, I don't give a shit about that 25th bit because it's not negative. So here is some code. For I in range 0 to 256, which of course excludes 256, I say give me the hundreds pattern, which is digits, that list, where each index in that list corresponds to the bit pattern for each index's value. And I do I divided by 100 mod 10, bit shift to the left 16. I divided by 10 mod 10, bit shift to the 8. I divided by 1, not necessary. Mod 10, bit shift to the left 0, not necessary, but it's there. I included the divided by 1 and the 0 for like consistency and clarity, right? It's showing my intention, right? Bit shift to the left 0, yeah, I'm bit shifting the necessary amount each time. That's why I included that. Cool. So this loop right here, I will have a list of 256 values corresponding to the bit patterns for each of these things. And I don't know about you, but I think that's pretty cool, right? Now, listen. I could have written this script probably a lot simpler. I could have probably done it with like just concatenating strings of bit patterns. I could have done it like that, right? But I'm doing it this way specifically so we're thinking about what the operations are and what we really need to get done. It's more close to like the hardware. Concatenating strings, that's a fairly abstract thing, right? Here, bit shifting values, yeah, that's lower level. Okay, so like I'm intentionally doing things at a lower level where it might feel a little like contrived, but it's very intentional. Just FYI. So for signed integers, well, we're going to do the same idea, but we have to be, keep in mind 2's complement, right? Okay, so we've got the first 256 and the next 256, which really is a group of 128 followed by another group of 128, right? The 128 positive numbers followed by 128 negative numbers, right? Right. So the same idea is used for the signed integers, but follows the 2's complement pattern, okay? And we need that sign bit. So you'll notice here, for I in range 0 through 128, it's the exact same thing, okay? Yeah? Yeah. But then here, I'm doing from negative 128 to 0. And if you're saying, well, whoa, why not like negative 128 to 0? Remember, the 2's complement bit patterns follow, like if this was 2's complement here, like 0, 0, 0, 0, 0, 1, 1, 1. So what, that's 7, right? Remember that 1, 0, 0, 0 is negative 8. And 1, 1, 1, 1 is negative 1, right? Remember that. That's how 2's complement worked. So that's why I'm starting at the most negative number, working towards 0. But again, in that loop, go to 0, but don't include 0. So really, this will go from negative 128 to negative 1. It all checks out. So continue the same thing, except this time also include that negation pattern in the ORs. And we move it to the left 24 bits. Cool? So now I have the unsigned 3-digit pattern and the signed 3-digit pattern. I now need to write these to a hex file. And the order is just going to be, because that leading sign signal, that like thing that's kind of acting like a multiplexer, a select signal, The first 128 or 256 will be the unsigned, followed by the signed. Cool? Cool. Okay, since there are two okay, the lookup table, all signed, yeah, okay. Yeah, so, okay, this is me just going on about the signed signal, right? I already talked about this. I could have two 8-bit ones and then have a multiplexer saying, well, which one do we want to output? What, should I output the one coming from the unsigned or the one from the signed, depending on this signal, right? This is what we're achieving. But really, we're just, shoving it together, right? We already talked about this. This is the idea, okay? Yeah. So notice how the configuration, the meaning of the input signals differ. The first 8-bit represents some binary number, and that 9th bit is not part of the binary number, but represents some like control signal. So the meaning of the inputs are different. That's what I was kind of getting at over there with the X, Y's, and Z's. Where, yeah, it's all part of the input signal to the lookup table, but what it means is different. So how do we save this to a hex file? Pretty easy. I mean, we got a lot of options in Python, but here's one. Create a file, .hex, write. We have to start with write, okay, v2, raw, whatever. And then I'm just saying, okay, write lines, the hex pattern. Now, by the way, this is important. Python, if you say print an int, by default, it shows you a decimal int. But I don't want the decimal, I want the hex patterns. So I just say like hex of the integer, and Python will like render it as the string as if it was a hex encoding, by the way. Same with bin. If you do bin of a number, it works the same way. Do you believe me? Cool. If you don't, you can try it for yourself. So I write all the lines from the unsigned patterns, and then all the lines from the signed patterns. They're stacked, we're done. Then all I have to do is right-click that lookup table, data, load the hex file, and I'm all set. Pretty cool. And let's discard memory output. There, right? So if we go here, edit, these are all the patterns, right? They're all there. There is a hex file. Here, where is it? It's probably on desktop. Here. Site, topics, output. One of these is a hex. Ah! 7-segment display lookup. Ah, look at this time it wanted it in Notepad++. There. They're all there. Now, with the hex file, you don't need to precede it with OX. You don't need to, but if you do, great. Personally, I like them to be there because it resolves ambiguity. Now, if you see the number, like if we go back here, you look at this and you're like, yeah, okay, but there's no ambiguity. There's an F there. But what if you, like, if you only saw a 6, okay, sure, it's the value 6, but what if you saw like 66, right? Well, what does that mean? Well, it depends if it's hex or not. If OX is there, it's pretty darn clear. And by the way, in Python, when you say hex, it will include the OX. So that's why it's there. So it's better that way, in my opinion. So here they are. And there should be 512 plus 1 plus 2, 514 rows. 513, uh-oh. 512. No, that makes sense, because the first row is V2, right? But it actually only goes from 0 to 5. So, but we do include the 512, yeah. So that makes sense. So really, it should be 0 to 511. But we have another one because it starts counting at 1, not 0. And then another one because we have that V2.0 space raw, right? Because of Intel. I could be wrong. I'm sorry, Intel, if you're watching. Maybe it wasn't their fault. So there we go. And if we go here, let's go here. Okay. Run. What number we want? Let's do this one. 170. But, boom, look at that. Now it's the signed version. But you may notice that if it's this, it doesn't matter because again, well, it's fine. Oh, look at that. Isn't that nice? Yeah. Any last questions? Pretty cool stuff, I'd say. So the next step, of course, is we got to get this into our into the ESAP system. Yeah? All right, we'll pick up here Tuesday.